have started this. You're going to note they're giving you a graph of f. They're giving you the tangent line at 6, which allows us to find f prime at 6. And then they're giving you values of f double prime and f triple prime. Okay, hang on, I got to shut this door. Okay. Stinky kids are all talking to me. All right. So we want the 4th degree Taylor polynomial for g about 3. So that means we need g of 3, remember this? But g of 3 is just the integral from 3 to 3, which automatically is 0. We need g prime of 3, which happens to be f of 2x, which is f of 6, which they happen to tell me is also 0. That's coming from the graph over here, right? This is a graph of f. We also need g double prime at 3. But that's just, so now we got to worry about the stinking chain rule happening here, right? Because g prime of x is really f of 2x. Everybody okay on that? But g double prime of x is 2 f prime of 2x, which is 2 f prime of 6, which we got to find from this tangent line deuter over here. And the tangent line, you can see, has a slope. It goes over 1 and up 2. So the derivative at 6 must be 2. So 2 times f prime of 6 is 2 times 2, right? Which is 4. Again, let me know if I mess up. I'm trying to get everything super sweet here. This is really an x here, I guess, if you want to think like that. All right, so this is g double prime at 3. I just plug the 3 in. So g triple prime of x is 4 f double prime of x. No, of 2x, right? Which means g triple prime at 3 is 4 times f double prime of 6, which is a 3. So that's a 12. And then the 4th derivative following the same exact rules here, we're going to get 8 times the 3rd derivative of f of 2x. So the 4th derivative, at 3 is 8 times the 3rd derivative of f at 6, which they tell me is negative 2. Negative 2. So that's just negative 16. Okay, all we're doing is building this thing. So A, let me see here, how far down does this go? I'll write it over here. But A says, what, with the 4th degree? So the answer to A would be that g of x is approximately equal to, I'm going to call it p sub 4 of x for fun, the 4th degree. But the first term is 0. You don't have to write that, but you can. The second one is 0 divided by 1 factorial times x minus 3. I'm just plugging it in. You can skip that. That's just a 0. I'm just writing out the pattern, okay? The next one is the second derivative at 3, which was 4. So that's 4 over 2 factorial, x minus 3 squared. Plus, we need the 3rd derivative, which we said was 12. So that's 12 over 3 factorial, x minus 3 cubed. And then minus was at 16, so 16 over 4 factorial, x minus 3 to the 4th. Okay, and that's a totally fine answer, but I'm going to simplify that just in case you want me to use it later on. I don't even know what B is going to ask us here. Blah, blah, blah. Write the x-coordinate of each critical point of G. Really? Okay, we'll come back to that. So, g of x is this polynomial, which simplifies all the way down to 4 over 2 factorial is just 2. So that's an x minus 3 squared. Simplifying it sometimes shows it's like a geometric thing or something. Plus 3 factorial, like right here, that's a 6 on the bottom. So 12 over 6 is also a 2, right? X minus 3 cubed. And 4 factorial is 24. So it's actually a 16 over a 24, which is a 2/3. X minus 3 to the 4th. So that's our 4th degree polynomial. It does not look geometric. But that's that. That's all it asks us to do, right? That's it. Okay. So B. So I'm going to erase all these derivative things we did here. Also, just while I'm erasing this, updates. Let me think here. They're going to put out, I don't know if they're going to put out sample questions, but they're going to put out a sample way to upload your answers sometime, I think next week, or maybe the week after, so you can practice doing it. And it's something you definitely want to do. Go online. It'll be on the College Board site in that AP Classroom thing, I think. I'll double check that between now and then. But they're going to show you how to upload your answers, and you make sure you can do that. And they're also saying that they're giving the test in May. You know that. The makeups are in June, and if you have any computer issues or if you have scheduling issues, like you have a test, 2 different tests at the same exact time, then you have to take one in June. But they said there's going to be scheduling issues in June as well. Like, again, there's going to be tests that are at the same exact time, so you can't take them both. So they said you should take your test in May, if definitely, and June should just be used for extenuating circumstances. All right. So B says find the x coordinate of each critical point of G. It's classified as a relative min, relative max, or neither. So we find critical points, critical values, by deriving, right? So we're going to find G prime of x, which we already did. That's just f of 2x. You all remember how to derive an integral, right? You plug in the top times the derivative of what you plugged in. So it's technically this times 1 because we plugged an x in. And then minus, plug in the bottom limit, the lower limit, that'd be f of 6, but times the derivative of 3, which would be 0. So that boils all the way down to just f of 2x. Okay, and we need to know where is that going to be 0. So we don't know what f is, but we have a graph for it. And you can see that f will be 0 when the inside is -2 and when the inside is 6. So for us to have critical values on G, for G prime to be 0, I need the inside of f to be -2 or 6. Okay? That means I need 2x to either equal -2 or I need 2x to equal 6, which means x is either -1 or x is 3. Now, they gave us this interval right here. Okay, so they're both in that interval, so we need both. And they want us to classify as local min, or relative min, relative max, or neither. And that's all based on how the derivative is changing sign. And you can see when f goes through -2, it changes from positive to negative. So positive to negative there. So that's going to be a minimum on G. And when f passes through 6, that goes from negative to positive. So that's going to be a maximum at -2 and a minimum at 6. I don't know if I said that backwards or not. So we're going to write that. X equals -1. So here are our critical values, right? So you might want to write that, I guess. So crit values are that and that, right? So that's our first part. And then x equals -1 is a local, what do we say, max? Because, and don't say it, don't say the graph, name the function. G prime of x is what we're talking about here. Changes from positive to negative. And x equals 3 is a local or relative, they're the same as a relative min, because I said so. G prime of x changes from negative to positive. Okay, everybody good? Sounds like it. Okay. Given f prime of 3 is -1/2, evaluate this stinky old integral. Oh, okay. Well, let's check it out. Do we need parts for this? Why are they giving me G, the fourth derivative of G? Huh. Okay, well I'm running out of room here. Let me steal this. Dude, come here. Give me this. Kablow. Okay, so let's just roll all the way over here. All right, so f prime of 3 is -1/2, but the fourth derivative is going to give us like the third derivative. Oh, because they gave it to us though. Got it. Okay, so this is parts. So they're making it weird, but there's a polynomial x squared, and there's a function we can integrate, the fourth derivative of G. So we're going to have to let u equal x squared, which means dv is going to have to be the fourth derivative of G. Well, that means v is the third derivative of G, but du is 2x. As a matter of fact, since it's just x squared, we're going to do it twice. We could also just do like one of those, the tabular method. You guys remember that? So we could do parts twice, or we could do the tabular method, which is where you have a column for u and a column for your dv's, right? And you write out u's. It's going to be x squared, 2x, 2, 0. Change the sign of every other one of them. So positive, leave, change, change. So negative 0, technically, if you want to think of it like that, right? And then over here, you're going to have the fourth derivative, cool, which is going to lead us to the third derivative, which is going to lead us to the second derivative, which is going to lead us to the first derivative. And you pair them up like this. So this integral is actually x squared times the third derivative of g, which we wrote out somewhere and I erased very cleverly, minus 2x times the second derivative of g, plus 2g prime of x. And we want to know what that is from 1.5, which is 3/2, to 3. So hopefully everybody's okay on the parts thing going on there. And we got to plug in the 3, so it's going to be 9 g triple prime of 3 minus 6 g double prime of 3 plus 2 g prime of 3. That's that part. And then minus, let's give me some more room here. 3/2 squared is 9/4. And then we need g triple prime of 3/2. We're subtracting all this. Minus 2 times that 3/2 is a 3. Then we need g double prime of 3/2 plus 2 times g prime of 3/2. So we got some hunting to do here. We got to find all this junk. And I forget what g even was. I think g was this. The integral from somewhere to x of f of 2t dt, right? For 3, right? It was a 3. Okay. So we already said this, g prime of x was f of 2x. What we got to get up to the third derivative? G double prime of x, I erased this, I don't know why, was 2f prime of 2x, and g triple prime of x is 4f double prime of x. Yo. So that's what we need. We need that at 3 and at 3/2. And we found all this stuff at 3 for the first question, actually. But we'll go through and do it again here. G double prime of 3, or G triple prime of 3. G triple prime, goodness gracious, of 3. Oh, there's a 2 on that x, right? Why don't you guys tell me that? I told you, call me out. Is 4f double prime of 6, which we did before, but I forget what it was. So let me steal this whole table too. I must sound like a maniac. Okay. Here we go. Zoom out some more. Where's this table going to fit? Right here? That'll be a nice little home for it. Yo, you're so small, table. There we go. All right. So I forget where I was even. We're plugging a 3 into this thing. That's f double prime of 6. Yes, which is 3, but times 4. So this is this 9 times 12? If you're with me, and again, I'm messing up, please let me know. This is 6 times g double prime of 3, which is 2f prime of 6. F prime of 6, that was 2, wasn't it? So it's 2 times 2, that's a 4. Remember, that came from the tangent line, right? F prime of 6. Remember, we had this tangent line over here? It's a little blurry. But the slope at 6 was 2. So the derivative at 6, f prime of 6 was 2. Here's what's going on there. Okay, we got all this. I think these questions are a little bit overkill. If you're seeing this, you're like, yo, this is a ton of work. I think the types of questions are important to be able to do. I think the AP test is going to be a little less involved than these, I hope. But they are going to make the AP test. They're saying, like, you might not finish. Don't worry about that. There's no limit to 3s, 4s, 5s. You just need to get a certain number of points. So you don't finish a question, just like last year on the AB test, don't stress too much. But anyway, we got that, and then it's plus 2 times g prime of 3 but that's f of 6, which I believe was 0. So that's the first part there. Minus 9/4 g triple prime of 3 halves is 4 times f double prime of 3. F double prime of 3 is 4. So it's 4 times 4, which is 16. Minus 3 g double prime of 3 halves. G double prime of 3 halves is f prime of 3 times 2. Well, f prime of 3, they don't give me in the table, but they told me f prime of 3 is negative a half. They told me that over here in part C. So it's 3 times, what did I say, just negative half, is that it? No. I've lost track of what I'm doing here, kids. I'm plugging into this right here, right? So it's 3 times g double prime of 3 halves, which is 2 times f prime. Okay, and 2 times f prime of 3, that's negative half. 2 times negative half is negative 1. So that's a negative 1 there, not a negative a half. All right, plus 2 times g prime of 3 halves. Well, g prime is just f, so that's f of 3 is what that would be. And f of 3, we gotta go all the way back to this stupid graph. They give me the point there. It's blurry. F of 3 is negative 1. Okay, just straight off the graph. So you can see they gave me in the table everything I needed, or they gave me like on the graph. I forget what it was already. Was it negative 1? So it's 2 times negative 1. And we can simplify this all out. We don't really have to. 9 times 12 is 108. And I actually would not. I would actually leave my answer like this if I were you guys. Because then there's no chance of you messing up anything. Like arithmetic, I mean, not anything. But it would be 108 minus 24. And you could put this all together if you want. That's this part. Minus 9/4 times 16 is 36. Plus 3 minus 2. And you can put that all together if you want, but I'm not going to do all that. Okay? So that was that thing. Be on the lookout for parts. Let's keep going here. Okay. D gives us some kind of a, I'm going to erase all this junk, new series. I don't know if it has anything to do with the other stuff we've been looking at yet. D gives us a divergent geometric series. Then it asks if this new series divided by n factorial is going to converge or diverge. Well, I'm hoping you know it's going to converge because n factorial is going to crush that thing down. Okay? But we're going to use the ratio test or something along those lines, probably. So, but the fact that it's a geometric series means that, and they say explain, I don't think they'll give you something this random like this. Like they'll give you a series, not like just a sub n in there. But so pretend instead of them saying, hey, it's a sub n, pretend they gave you like an actual geometric series, but it's divergent. So all that means is you have some initial term a, and you have your ratio r to the n minus 1 like that. Actually, if we start at 0, we can just have this be r to the n. That's what it would be, right? It'd be a number times some number to the nth power. And all we know since it's divergent is that r is either 1 or bigger than 1. Okay, it can't be less than 1 because like the absolute value of it can't be less than 1. Oh no. Okay, let's plug in over here at the bar. And when I say the bar, it's because I have this like big wooden bar thing in my sunroom. I'm not at a bar, obviously. All right. But that's divergent. But the series they're giving us then would be this. This is what they're really asking about. A sub n, which is ar to the n, and we're dividing that by n factorial. And all we're going to do is use the ratio test to show that it converges. Okay? So let's erase all this old junk that I wrote over here. Get out of here, old junk. Goodbye, 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 goodbye. Okay. So using the ratio test, it's going to look like this. We need the n plus 1 term, which is this. And we would divide that by the nth term, but we always say you always multiply by the reciprocal. We don't divide, we multiply by the reciprocal. And we get that. And like we saw last week, I believe, the exponential stuff, like the geometric stuff, is going to reduce all the way down. and leave us just with an r. But the factorial is going to leave an n plus 1 on the bottom there, and this limit is 0, which is less than 1. So it's going to converge. It's going to converge by the ratio test. I wonder if my kids, hang on one second. Are you guys good? Okay.
They are not good.
They got done their Lexia writing, whatever it is, language arts work. But anyway, I hope that makes sense. Now they're giving us this B sub n sequence. So they tell us what B of 1 is, then we can find these other ones. Find the third partial sum of the series. Okay, that means we want, again, add up the first 3 things. All right, so let's go ahead and do that. The third partial sum is the first term, which is 1, right? So 1 plus the second term, which we get by plugging into here. Now, if I want the second term, pay attention to n here. If I want b sub 2, that's really b of 1 plus 1. So n is 1 in this case. Okay, it's really b sub 2, but n is 1 to get b sub 2. So that turns this into 1 plus 1 to the first times b sub 1. Well, that's just a 2 times 1, so it's 2 plus. Then to get b sub 3, I need to plug a 2 in, so it's b sub 2 plus 1, which is b sub 3, but n is really 2, so it's 1 plus 1/2 squared times b sub 2. And b sub 2 was 2. So 1 plus 1/2 is 3/2, squared is 9/4, I believe, and times 2 is 9/2. So that would be 2/2 plus 4/2, which is 6/2, plus 9/2 is 15/2. That's the third partial sum. Then they wanted to use the ratio test of this thing. So ratio test is going to look like this. It's the limit as n goes to infinity, there you go, of the n plus 1 term, which is this, right? So that's plus 1 over n to the n times b sub n. Oh, no, we need the n plus 1 term, right? Yeah, that is the n plus 1 term. Okay, they gave us that formula for it. Okay, so they're not n plus 1s in there, which is weird. The n plus 1 term is just that. They gave us the formula. And we're going to divide that by the nth term. And normally we multiply by the reciprocal of it, but the nth term is just, oh my goodness, look at this craziness, b sub n. So I don't know if this seems scary to you guys or not. It's going to end up being really easy. These b sub n's cancel out there. Okay, so again, this is the b sub n plus 1 term divided by the nth term. That's what the ratio test says to do. And this looks complicated, more complicated than what we've done before because there's nothing really to plug into. That's because they gave us these formulas. So this boils all the way down to this. Okay. And we could go ahead and do L'Hopital's rule with this, right? But do you guys know what that limit is? Anybody know what that limit is? Someone talk to me. We've done this limit.
E.
Yeah, that's E. And it turns out E is greater than 1. So it diverges.
11.
No. Diverges by the ratio test. Woo! How is that? You're on your way to a 5, kids. Oh, there's coffee right here. Excellent. Okay. So that's the whole thing. Questions on this? I don't know if there's any comments in our little section here. I don't know if I'm putting you guys to sleep. 55? Oh my God. It's like reading a novel. Is there anything good in here, or are you guys just making fun of me?
Read them all and you'll see.
Why is it E? Yes. How do I know that? Very good. Bet more money for trucks. I can't. What comes after the alphabet? What? I don't know. How many parts are they going to put on there? Yeah, I don't know. Don't worry about it. Yeah, that's true. Okay, good enough. I don't know if there's anything else coming in here. I keep trying to pause you. I'm sorry. This is a video. I will drop this into YouTube, okay? Colin is staring into a soul. I see that. Very good. Alex, very helpful. Isn't it x minus c to the n? Wait, I think I'm just dumb. What? Okay. Yeah. The top of my head. Okay. So it's E because who made this question? I don't know. So all the BC teachers got together and I've shared nothing. I've done nothing to help the group. But some teachers have had made resources or found resources through a college board thing. So they just shared. We have a big Google Drive shared folder, and this was in there, and I thought it looked good. So anyway, the reason why this limits E, so this is definitely important because you can expect L'Hopital's rule to happen here, okay? So if you have a limit, we spend some time doing this, all right? If you try to plug infinity into that, you're going to get 1 plus 0. Now remember, it approaches this. It doesn't equal this, raised to the infinity, which is 1 to the infinity, okay? But it's close to 1. It's something real close to 1, so 1 plus. So something a little bigger than 1 raised to the infinity. Okay, and we said that could either go to infinity since you're multiplying something by itself that's bigger than 1. It could go to some number in between infinity, and it could go to 1. We don't know. All right, we don't know unless we do L'Hopital's rule, but we can't do L'Hopital's rule unless we do this fancy little trick. It's an exponential one, so we're going to say, hey, let's move you out of the way for a second. Get out of here, Lim. We're going to say, hey, let's rewrite it like this, e to the ln of all this junk. Right? Because that's still the same thing, but that allows us to do this e to the limit as n goes to infinity of the ln of 1 plus 1 over n. Now, really, you bring the n down. That's what ln lets you do. But we said you're going to make it a fraction like that. And if you do L'Hopital's rule through there, and even on the AP test, you got to say we're allowed to use L'Hopital's rule because, so you got to write something like this, since the limit as n goes to infinity of ln of 1 plus 1 over n is 0, and the limit as n goes to infinity of 1 over n is 0, I can use L'Hopital's rule. Yay. All right. So then you actually do it. So this limit is equal to, it's still e, it's still the limit in the exponent because of the way we wrote things, but you get 1 over 1 plus 1 over n. That's the derivative ln times the derivative of the inside, which is negative 1 over n squared, all over 1 over n squared. And all this junk cancels out. Goodbye. And as n goes to infinity, you get e to the first power. That's why it's e. All right.
So on the AP test, if you just write that it's e, if you just already knew that, would that be okay, or should you do L'Hopital's?
Oh, man, that's a good question. I don't think they're just going to give you E because, that's the one you're supposed to know, I think. If I had time, I would do L'Hopital's rule. I would show it. Okay? Although I do think that could just be considered common knowledge. All right? But just to be safe, I would do it. But I doubt they're going to give you, that basic of an example. They're going to give you one that you're not going to be sure what it turns out to be. All right. You heard what I said. Whoever made this test, your questions are basic. All right. Now, I've got this bad mamma jamma. This is a logistic model. Remember, we learned that, right? It looks like, just by looking at the slope field, that the carrying capacity is 10, right? That's M. Cool. Can you guys see me like this? I don't want to make weird faces. Let me see. All right. You can see the top of my shiny head. Okay. All right. I got to put this down lower anyway. Right on. Use Euler's method with 2 steps of equal size, blah, 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 to approximate f2 in terms of k. So Euler's method should be relatively simple as long as you remember it. Now, you can look this up. Other teachers do this differently. I like to make a little table with our step, with our x value at that step, our y value at that step, our derivative at that step, and our change in y at that step. So at step 0, we're starting, we want to approximate f of 2, and we have to use the point they gave us, which is 0, 1. So we're starting with 0, 1. Okay, the derivative there. Oh, in terms of k, so you're supposed to know what m is, I guess. Let me read this again here. dy dx is ky m minus y, has a slope field, blah, blah, blah. Let y equals a particular solution to this. F of 0 equals 1. Where's method of 2 steps? Okay, yeah, so you're supposed to know that m is 10. And the reason why we know m is 10 is because m is the carrying capacity, and that's where this curve flattens out. So remember, we're starting at 1. You can see this thing's going to go like this, sort of, and then flatten out like this. Cool. And if we started out above it, it would come down and look like this. Cool. So m is 10, which means dy dx is k times y, which is 1, times m, which is 10, minus 1, which is y. Okay, so that's just 9 times k. 9k. We also know we're taking 2 steps, and we're going from 0 to 1. So the change in y is always just the change in x times the derivative there. Okay, so since we're taking 2 steps and we have to get to 2 from 0, this change in x is just 1. So delta y is just 1 times 9k, which is 9k. So my new y value is 1 plus 9k, whatever that happens to be. All right, then we can find dy dx again. So that happens to be k times the y value, which is 1 plus 9k, times m, which is 10, minus 1, the y value, right, which is 1 plus 9k. What? That seems crazy, right? But we'll simplify that out. That's just k times 1 plus 9k times, all this is 9, minus 9k, right? We take a 9 out of there just to make this look a little simpler for us. So it's 9k times 1 plus 9k times 1 minus 9k. That's not too bad, right? And this is just the difference of 2 squares there, so this becomes 1 minus 81k squared times 9k. And do they want us to actually write this out? This seems like a little much. Am I messing this up? You guys see anything here? That's 9k minus 729k cubed. Whoa. Right? Yeah. Okay. So that's what the derivative is there. 9k minus 729k cubed, which means change in y is just that number again because delta x is 1. So we have to add that to what we had. So it's 1 plus 9k and 9k are going to give me an 18k, and then minus 729k cubed. So get out of here, bar. There we go. That seems a little bit much too. Again, the idea behind it, you should be able to do Euler's method, even if they give you a variable that's in there. That shouldn't be too bad. But that just seems like a little bit much arithmetic-wise. All right. So find the second derivative of 0 at 0 in terms of k and y. Y in terms of k and y. We know what y is at 0. Whatever. So we have to derive this thing. Okay. So the second derivative. So this is all part A. Oh, we got to write this out, right? So f of 2. So we got to answer part A is approximately 1 plus 18k minus 729k cubed. Whoa. B. Find the second derivative in terms of k and y. Well, we're just going to derive this dumb thing, right? So we get d squared y over dx squared. Happens to be, by product rule, k dy dx times m minus y plus. So we're doing product rule because if you look up here, there's a ky and there's an m minus y. So we're multiplying those two things. So when we derive them, that y does not turn into a 1, it turns into its derivative, dy dx. So deriving ky yields a k dy dx times the second part, m minus y, plus, leave the first part, ky, times m minus y's derivative, which is negative dy dx. And you can see from here, we got to plug in what dy dx is, because the question specifically says, what is it in terms of k and y? Not dy dx. We don't want that floating around. But before I plug anything in, I'm going to simplify. There's only 2 terms here, right? There's this big thing and there's this thing. From both of them, we can take out a k and a dy dx. All right, that's going to leave us with an m minus y minus y. Okay, because there's a negative right here, and we're taking away the dy dx and the k, so that just leaves a negative y there. And the other m minus y is coming from right here. Okay. So that is k times dy dx, which happened to be ky times m minus y, right? That's what that is. True? Yeah, that's logistic, right? Yeah, come on, Glenn. Times m minus 2y. So that is the second derivative. Oh, it's in terms of k and y, so we can't leave this dumb m in here. That's just a 10. There we go. Okay, and by the way, we did this in class a long time ago, but that's why logistic curves have a point of inflection at half of their carrying capacity, because when you drive a logistic curve, you always get this piece here, and that will always be 0 when y is half the carrying capacity, and that's where that point of inflection comes from. Okay, so is that all it asked for? B. Yeah, find f double prime, y is f of x, okay, of 0 in terms of k and y. So we got that. All right. So again, but they tell us that f of 0 is 1. So I don't know why they just let us plug the 1 in there, but whatever. The actual value of f of 2 is less than 4.6. Is your answer in part A an underestimate or an overestimate? Well, why are they telling us 4.6 then? Oh, just so we know it's below 5. Okay, so Euler's method, the whole over or underestimate depends upon the concavity of the curve. Okay, so let's take a little sidebar over here. If you have a curve that's concave up and you use Euler's method, all you're really doing, now you don't know what the curve looks like, but all you're doing is moving along the tangent line when you do this, and you keep readjusting as you go. Okay, so if the curve is concave up, then you have an underestimate because your tangent line is always underneath of it. But if your curve is concave down and you do Euler's method, you're going to move above the curve because the slope is decreasing, but your tangent line does not have a decreasing slope. Woo. So that's why it's telling us that 2 is less than 4.6. They don't have to say 4.6. They have to basically let it be less than 5, but they just picked 4.6 to make it look weird. So because f of 2 is less than 4.6, we know our logistic curve is concave up. Because there's a point of inflection at 5, right? Remember? Logistic curves look like this: concave up, and then concave down. Cool. But they made us find the second derivative, so we should use that. So d squared y over dx squared. Because we know that, I don't know what they want us to write here for this whole thing, because we know f of 2 is less than this. So I'm just going to say that it's positive. Like they might want you to show this by plugging into this stupid derivative here. Like you put a 1 in there, it's positive. You put a 4.6 in there, it's positive. So it's positive the whole time, basically. Okay. But the second derivative is positive on the interval from 0 to 2. And that's what matters, because we started at 0 and we moved to 2. So we want to say that it's positive that whole time. Okay. So y is concave up. And our estimate is then an under approximation. And that's all I gotta say. Approximation. There you go. What? Okay, approximation. Woohoo. Okay, we're almost done. This isn't too bad. It says justify your response. That's what we just did. Again, you might want to find the second derivative at 2 and at 0. All right, and then last part, they say y equals g of x is a particular solution to the differential equation. All that means is the derivative of g is this. Okay, you know that g of 1 is 12. All right, and they want to know as we go to infinity, we have to find this. So let me snag this whole question again down here. That's not what I want to do. There we go. That's what I want to do. Boom. I'm just giving myself space down here. That's all. Okay. You guys still with me? No, I know we're over time. You're welcome. I'm working extra hard. So we want this limit. So I'm going to write that out again. The limit as x goes to infinity is g of x minus 10 over f of x minus 10. Now, here's what they're doing to us. This is a L'Hopital's rule situation, my friends. because as you go to infinity, because these curves are logistic, but they satisfy this differential equation, and the carrying capacity is 10, it doesn't matter that g of 1 is 12. Like, so all they're doing, they're saying that's starting out above the carrying capacity up here, but it's just going to go right down to 10. Okay? So as we put infinity, both those functions go to 10 because they're both solutions to the differential equation that was logistic with the carrying capacity of 10. So we need to write that out. The limit as x goes to infinity of g of x minus 10 is 0. And so remember, you can't just write equals 0 over 0. That's a big thing. As we approach infinity, the denominator also approaches 0. So dot, 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 I can use L'Hopital's rule. Cool. And then boom, do it. It's the limit as x goes to infinity. Get out of here. Get out of here. What? Why aren't you? You see my computer screen right now, right? Why isn't that erasing? Like this is like permanently on my screen. Whatever. So when you derive that, you're going to get g prime of x over f prime of x, right? However, we happen to know that g prime and f prime are both k g of x. Now it's y, but in the case of g of x, it's g of x there times 10 minus g of x over k f of x is 10 minus f of x. Cool. But again, as we approach infinity, oh man, this is going to be 0 over 0 again, right? Yeah. Huh. Why do they tell me g of 1 is 12? Does that matter? You're going to get 0 over 0 again because you got that stupid thing. They can't want you to derive this again. That seems crazy, right? I mean, the k's cancel out. Let me look at this guy's answer key. If you want you to do L'Hopital's rule again. Unless I'm missed. Do you guys see me missing anything? Let's go all the way down to this question here. Wait a minute. He just says that equals 1? I don't like that. Because they're different functions, right? Why does this equal 1? 10 minus y and 10 minus y. Huh. I don't know about that. Okay. He's saying it equals 1. I got to think about this. So we got to the part here, but he's just saying they equal y. But y is like any function at all, basically. And we have two different functions. One's f and one's g. What are you guys saying to me in this chat? Am I missing something? Like their slope should be approaching the same thing? Yeah, he just leaves them as y, but they're different functions. But their slope, I mean, their slopes are both going to 0, I guess at the same rate the further out you go. So it makes sense that it's going to be 1. I just feel like we should derive that thing again. Which is going to be kind of a mess. Yeah, he just leaves these as y's in here. But I don't like that. I got to think about this right now, okay? Again, you'll see L'Hopital's rule. I don't think you'll see it like this, but that's what they're doing in their answer key. And I'm saying he because the other test I have was from this guy named Brian, like Passwater or something. But this could be a female teacher. I'm sorry, I don't know who made these questions. Anyway, I'll double check on that. But that's the basic gist of it. Okay, I'm a little unsure about this. I need to check it out. But we'll just say it's 1 for right now. I mean, it makes sense that it should be 1 because they're just the derivatives and they're both going to approach the same thing. But I don't know. Let me think about it. Either way, that's those first two questions there. Okay? I know I've given you more. I'm going to stop recording since I'm just kind of rambling